Welcome back. In this video, we're going to be taking a look at a problem involving the light passing through a thin lens. And in these types of problems, we'll typically approach them in two different ways. First, graphically by drawing the principal rays coming off the object towards the image, and then numerically by using the thin lens equation to calculate the missing quantities. So keeping this in mind, why don't you go ahead and read through the problem statement. So what we have in this problem is an object, and then it tells us that the image is apparently inverted from the object. It's a real image, and it tells us the distance between the object and the image, but we don't know where the lens is. We also know that the object is twice as tall as the image, and the questions it asks us are what type of lens are we looking at here, what is the distance between the object and the lens, and then finally what is the focal length of the lens. So the first thing you always want to do, I think, is just kind of look at this thing graphically and draw the principal rays. And so what I mean by principal rays are, well, if you look at the object, and I've redrawn this thing over here, so we can just kind of sketch over here, this object has light emanating from every single part of it. So in other words, at the very top of it, there's light going in all directions. Right here, there's light going in all directions. Here, there's light going in all directions in general. And what's going to happen is that light's going to move somewhere in this direction. And if there's a lens there, even though it's all diverging in different directions from a single point, that lens may allow all that diverging light to converge back to a single point over here. And if that occurs, then you may get basically a copy of this object over here, which is known as the image. Now, that depends on what kind of lens we're looking at. In this case, we know it's a real image and it's inverted. And that can only happen when you have a convergent lens. Only convergent lenses will produce real images. So we know we do have a convergent lens here. And so what we can do is use some ideas from what the principal rays look like from an object to an image in a convergent lens. Now, to draw these principal rays, the way we do it in practice, a principal ray is just a couple of all those rays. So it's the rays that will be enough to tell us what the relationship between the object, the image, and the lens. And there's only 3 of them, and we only look at the top part of the image. But I just want you to keep in mind that there is light coming from everywhere else. We just don't draw those rays because they don't tell us any more information. Now, the first principal ray is the one that always goes through the middle of the lens, and it just goes directly without refracting. In other words, it does refract, but on the first part of the lens it refracts in, and the next part it refracts out, and those cancel out, so it kind of just makes a parallel, more or less a straight line. So we're going to draw that one. Now it's always going to go from, basically you want to get all the principal rays from the object, top of the object, to end up at the bottom, at the other part of the image, the corresponding part of the image. So the first principal ray we're going to draw is the one that goes straight through, and I'll try to draw it as straight as I can here. All right, so we know that because it's going to pass through the middle of the lens, that the lens has to be right there. So let me go ahead and draw the lens in. All right, so there's our lens. Let me go ahead and draw the other 2 principal rays that you want to draw for these types of diagrams. The other one, the second one, is the ray that comes parallel from this. So again, light's coming out in all directions. We've already drawn this one, which we know is going to pass straight through the lens. It's going to refract a little bit this way and then back out towards the image, towards the head of the image. Now the one that comes in parallel towards the lens always goes through the focal point and ends up there. The focal point, we don't know where it is, but if we just draw that and make it converge to this point here, it'll tell us where the focal point is. So that one's always going to go through the focal point, the far focal point. So that tells us now that the focal point of the lens is right here. Similarly, if we look in the opposite way, the one that goes to the focal point on this side of the lens will come out parallel. So that one, I need to make it basically come out parallel. So let me draw the parallel part first. Okay. And that one has to go through the focal point in this direction. So it'll look something like this. And that tells us that the focal point on this side of the lens is right there. And those numbers have to be equal. So if you draw in an image and they look like these guys are kind of very different than the image, you need to tweak your image and just draw it a little better. And again, these are just 3 principal rays. I could draw a bunch of other rays coming through, but there's no hard and set rule for how they pass through the other parts of this picture. Okay, so given this, now we need to find out, we know that it's convergent lens. We need to find out what is the distance between the object and the lens. So this distance right here. Let me label all these things with the values they use in your book. So the distance between The object and the lens is called P. The distance between the lens and the image is called I. And then the distance between the focal point and the lens is, the center of the lens is called F. And these are both, they should both be equals. These are both F. All right, so what we're looking for here is P. We want to find the distance between the object and the lens. And there's two ways to do it, actually, in this problem. We can use the thin lens formula, or we can also actually use similar triangles. So I'm going to have you guys do that first. We're going to use similar triangles. Let me point out which triangles I'm talking about here that are similar. The one that I'm talking about here is that this triangle, which is spanned by the object, P, and this principal ray, is similar to this big one, which is spanned by this distance between the object and the image. And the reason I want to use that similar triangle is because we know that distance is d. So in other words, this right triangle is similar to this right triangle. If you use the fact that they're similar, you can solve for the missing quantity, which is P. So go ahead and try that out real quick, and then we'll come back and look at that answer, and then use the thin lens formula to just check that, and then we'll finish up the problem. So here I've drawn the two similar triangles inside of one here. And the large triangle has, the base of it is d, the full distance between the object and the image. The smaller triangle, the distance between the object and the focal point is P, which is what we're looking for. And then I need to know these sides to use similarity. What we do know is that the image height is half the height of the object. So I just need to put numbers here which are off by a factor of 2. It doesn't matter what the actual units are because we're using ratios. So if this is 1, for example, that'll be 2. Now, just using similarity, I know that 2 over P must equal 3 over D. And since we know that D is 40, that easily tells us by cross-multiplying that P is 26.7 centimeters. And you can verify real quick, this is exactly 2/3 of the full distance, which kind of makes sense with our picture. Finally, we can verify this with the magnification formula. So the magnification formula says that the magnification in a single thin lens scenario is given by the distance of the image to the lens divided by the distance of the object to the lens. But there's a minus sign there as well. So it's minus I over P. Okay. In this case, what's our magnification? Well, we know that the object height is half the image height is half the object height. It's also inverted, so that's going to give us a minus. So the magnification is minus a half. And then, well, we don't know I, but we do know that since the full distance is d and this is p, we can write I as d minus p. So that tells us that we have, just canceling out the halves here, I have d minus p over p equals 1/2. And if you solve that with the given d, you can once again verify that p equals 26.7. Okay, so that'll verify to you that these two ways we've solved this, one kind of more graphically, and one just using the magnification formula in a calculational sense to give us the exact same number. Right? So that's the distance between our object and our lens. Now let's go to the last part of the problem, which says what is the focal length of the lens? The focal length is the distance between the lens and this points that I've drawn here. And a lot of times they'll be given to you because once you know the focal length, you can draw the principal rays and find out if an object is placed over here, where the image will be on that side. In this case, we're kind of working backwards. So what we're going to use is the thin lens formula, which says that, this is the one that you're going to kind of use for all these problems, that 1 over P plus 1 over I equals 1 over F. Now this algebra is very straightforward, it's simple, but the only thing that tricks a lot of students is determining what the signs are of P, I, and F, because they can all be plus or minus. Let's first look at the focal length. So the focal length, that one is it's straightforward. Whenever you have a convergent lens, the focal length is positive by definition, and whenever you have a divergent lens, the focal length is negative by definition. This case is positive for us because we got a convergent lens. Now the image can also be plus or minus. If the image is real, it's plus. If it's virtual, it's minus. Now that's not always the case depending on the convergent lens, because convergent lenses can actually produce both real and virtual images. Divergent lenses will always produce virtual image. So you want to think about what type of image it is to get the sign of I. In this case we got real, so again it's positive. So let's plug in our values to find the focal length. P is 26.7, And I is, it's a full distance minus p, so it's 40 minus 26.7. And then that just equals 1 over f. So you can just invert that equation to find out what f is, and you should find that the focal length is 8.89 centimeters. All right. And now in our picture, you always kind of want to make sure your numbers make sense with your picture. You've drawn the picture to help you with this problem, and you can always verify things with that. So we know that this full distance here is about 30 centimeters. Let's see, so this is about 10. Looks like about a third. So it kind of makes sense with our picture. And it is positive as we expected for a convergent lens. These are a couple of checks you can do. So that's the answer to the problem. I'm going to leave you guys with one more question, which is not on the problem statement, and that's the following. Say I moved my object to 4 centimeters away from the lens, but I didn't move the lens. All right, so now let's move the object closer to the lens. The object is here, and this distance is 4 centimeters. And then our focal length, of course, because I'm not changing the lens, the focal length as a property of the lens is going to be the same. So the focal length is 8.89, so the focal point is out here somewhere. And again, on the other side. I want you to draw what the image that this object would produce using this convergent lens. All right? This is a little trickier because now it's actually going to produce a virtual image. But go ahead and try to draw it out, and we'll come back and finish that up. So in this case, drawing out the principal rays once again, all the rays coming out of the top, there's 3 principal rays we can look at. So the first one goes straight through the lens, and that just maintains its trajectory. Okay. The second one, any ray which goes parallel towards the lens will always refract towards the focal point. It's got to go like that. All right, so again, this is a convergent lens, so all the rules that applied over here are going to apply over here, even though their object is in a different position. Now, the last one is the one that comes, in this case, remember it was going through the other side focal point, is going to come out parallel. So this, in this case, is kind of on this side. So now we're going to just imagine it's coming from the focal point towards the lens. So it's going to come like this. I'll just draw the dotted line to show you I made it from the focal point. That's going to always leave out parallel. Notice what we have here. We don't have these rays converging to a single point like they did in this case. And the reason is because the object is inside of the focal point. So what do? What we do here in this case is actually follow them backwards and see where they converge on this side of the lens. So what I'm going to do is follow this one backwards. So you always look on this side and follow them backwards. This is a big point of confusion for students. Don't follow these guys backwards. Follow the ones on this side backwards. And just in a straight line. So this one coming straight back is just going to maintain its parallel trajectory. Okay. This one coming back is going to maintain this trajectory. Okay. And then this one coming back is going to maintain its trajectory. And they should, if you draw this correctly, should all end up at the same point. All right. This is kind of tricky on your paper because if you don't draw it very well, they're going to meet it at different intersections. So just try to draw it as well as you can. Use a ruler if you need to. They all meet up over here, it looks like. So let me draw that in purple. And that'll be our virtual object. Our virtual image, rather. So this is the object, and this is the image. What does it mean that it's virtual? So in this case, what happened over here? We had all the light emanating from the single object, and it met up over here. And as I mentioned, that's going to create some kind of copy of this object over here. All right, so the light's actually meeting up somewhere, and you can capture that image somewhere like on a camera or on a like a photographic plate of some sort. In this case, that doesn't happen. So why are these useful? This is actually the situation we see much more in our real life. If we're over here on this side of the lens, what do we notice? Well, we see all this light coming from this top of the object, and it came through here, and then it all ended up over here, and our eyeball's over here somewhere. So we're capturing all these rays of light and everything in between. Our brain has no idea that it's coming and it changed trajectories. We think it all came from the same point. So we think all these rays of light came by going in a straight line. So we think that this ray of light started somewhere over here, this ray of light started somewhere over here, and this one started somewhere over here. So we actually think that all these rays of light came from the single point over here. So what we think we see is not this object, but this image. And this is how magnifying glasses and eyeglasses make things look bigger. The virtual image is what our brain thinks we see. And it only works if you're on this side of the lens. So this is the reason we draw virtual images in these types of problems, is it tells us the apparent image when you're on the opposite side of the lens based on a particular object. Keeping all that in mind, let me stop here, and if you have any further concerns or questions, take a look at the summary and the attached write-up. See you next time.